This is chapter 5, thermochemistry. Study of energy. The SI unit for energy is joule. Of course, you know how to transfer to kilojoule. You divide by 1,000. As it states here, energy can be transferred from one form to another. We have chemical energy, which we'll be focusing on in this chapter. For instance, a chemical energy, chemical reaction occurs, and then it gives off energy or releases energy. We have energy from the sun, we have electrical energy, we have mechanical energy, movement. So different forms, and they just transfer from one form to another. As I just said, thermochemistry, which we'll talk about in this chapter, involves the quantities of heat change during a chemical reaction, whether we absorb energy for a reaction to occur or whether we release energy for a chemical reaction to occur. Kinetic energy is the energy that matter possesses due to motion, and its opposite is potential energy, the energy that is stored. So for instance, if you have a hill and you have a ball on top of the hill, it has a lot of potential energy and not very much kinetic energy. The ball hasn't moved. If we extend the idea, now we have the hill and the ball is now rolling. We have lots of kinetic energy. The ball is moving. This is supposed to indicate movement. And we have very low potential energy in this instance. So we won't work too much with these two equations, E equals half mv squared, or E equals kqq over d. But just keep in mind the two ideas of kinetic energy and potential energy. We also classify in terms of types of systems: open system, closed system, isolated system. For open system, if we can look at the simple example of a cup of water, if we say that our system is the cup of water and everything around it is surrounding, we say this is an open system because if you let the water sit there for a long time, you will lose mass due to evaporation. You also have a transfer of energy. You assume if it's a cold cup of water, the energy from the surrounding, the atmospheric temperature, the heat will transfer from the outside to the inside, and the water will over time evaporate. We have something called a closed system, number 2. A water bottle is a nice example. No water can be lost, technically. If it's sealed properly, you can only have heat going in and out, but you will not lose any mass of water if it's in a closed system. And in the third system, we have an isolated system where there is no transfer of mass. You can't lose any water or gain any water. And technically, you can think of it as if it's a perfect isolated system, you can't lose any energy. If you put water in there, the temperature of the water would stay the same over time. Of course, that's an ideal situation. So in terms of transferring energy, it can be done through work. It can be done through heat as well. Work is described as the energy required to move an object against force. So W equals to force times distance. We also have heat, which is, as you guys know, heat travels from hot to cold objects. There must be a difference in temperatures between two things for heat to transfer. And we usually don't say there's a lot of heat on the stove. We usually say there's a high temperature on the stove. If I were to burn my hand, we can say all the heat transferred from the stove to my hand and burn my hand. So there are two ways. If I wanted to, for instance, if I wanted to heat up my hands, let's say under the sink, I can do some work and get energy into my hands by rubbing them together. So there's some work involved to heat up my hands or to add energy to my hands. And I can also do no work, and I can just heat up my hands by turning on the faucet, hot water, and the hot water will transfer from the water to my hands. The first law of thermodynamics, which we will focus on in this class, that energy can change from one form to another, but cannot be created or destroyed, we use the symbol E for internal energy. And the triangle here means change of. So we can say E2 minus E1, E final minus E1, and we'll talk about this later in the chapter. But if the E final is greater than the E initial, we say the system has gained energy from the surroundings. And conversely, if the value of delta E is negative, meaning that the initial value is greater than the final value, the system has lost energy to the surroundings. Here we have a graph of internal energy. So we had a reaction here of H2 plus O2. Yes, the equation is balanced. 4 H's on the left, 4 on the right, 2 oxygens on the left, 2 oxygens on the right. Here we just want to show that the reactants here have a particular energy state. So they have a particular energy. And if we were to make water, the net result is the energy will be lower for water than the initial reactants, meaning that the energy, this would be a loss of energy to the surroundings, and the delta E would be negative. Based on the first law of thermodynamics, if the system lost energy, the surrounding would have to absorb the energy. So let's say for this reaction to make water, it gives off energy. The surrounding would have to absorb that energy. We can also put together the heat for Q. W is work. Both units are joules. That's the SI unit for energy. We can say the change of energy can be defined by the heat and the work. So when heat is added to the system or work is done on the system, our way of explaining this is that the change of internal energy increases. This is the arbitrary way we describe internal energy increases when the system absorbs energy, and when, so it just says here, when Q is positive and W is positive, this both means that the energy from the surroundings comes to our system. So our cup of water, if the work is done on the system by the surrounding, we say W, work is positive. Endothermic reaction means that the system has absorbed some energy. So if we look at this reaction here in biology, this is photosynthesis, meaning that for photosynthesis to work, for the plant to give off oxygen, we need light. We need energy from the surrounding. We need light for this reaction to occur. We call this an endothermic reaction. If I want to go from water to steam, I need to add energy for the water to evaporate. Conversely, we have exothermic, meaning a reaction that releases heat from the system to the surroundings. So in this reaction, we have sodium plus water. It gives us sodium hydroxide, H2 gas, and energy. The Q value is negative because the starting materials have a higher energy than the product. Examples of exothermic reaction: when you have a strong acid plus a strong base, you put your hand on the beaker. If you add a strong acid and a strong base, you'll feel that the beaker is warm, meaning that it's giving off energy. If you light a match, that is also an exothermic reaction because you get heat, you get light from the match, so it gives off energy. I'm sure you guys can take a look here. Cooking an egg, is that a positive Q? Is that an endothermic reaction, or a negative Q, an exothermic reaction? That would be a positive Q for cooking an egg because you need to turn on, you need to have some heat source, whether it be a fire, whether it be turning on the stove, you need to add energy to cook an egg. And freezing water to ice, you need to release energy. For water to turn to ice, you need energy to be removed from the system and go to the surroundings. Mathematically, we can also express the change in energies, as I said earlier. E system is Q plus W. Q is heat, W is work. So the question here is a gas expands and does work on the surroundings equal to 350 joules. So the work will be 350. It says here it does work on the surroundings. So that would mean from our definition, or the way we define positive and negative, the W would be negative 350 joules. And if it absorbs energy here in terms of heat, it would be 114 joules. The Q would be positive. When we add the two numbers together, the change in internal energy is negative 236 joules. So it might take a while just to understand the wording. Absorbing heat is positive, releasing heat is negative. Again, doing work on the system is positive, doing work on the surroundings from the system is negative. In this case here, a system releases 15 kilojoules of heat and performs 890 joules of work on the surrounding. First, we should make sure these two are the same unit. So we want to convert this to joules. It's going to be 1500 joules. So we have 1500 joules. The system releases 1500 joules. That means it's negative heat, negative Q, performs 890 joules of work on the surroundings. So that's negative 890. If you add the two up, you'll get negative 15890 joules. You can pause the video now and try the next one. Again, these will be posted on the CUNY Blackboard Commons site for SEC 201. The question here reads, the change in internal energy was 166 joules. So if we have here E delta E equals Q plus W, the internal energy here would be 166. If 188 joules of work was done on the system, that's plus 188. And just use your math to figure out the value of Q. And that will come out to negative Q would equal to negative 22 joules, meaning the reaction would be exothermic in terms of the transfer of heat. State functions is something we just have to be cognizant about when we're studying the first law of thermodynamics. State functions is defined as the quantities that define values for given states of a system. So it doesn't matter what path we take. And what does that mean? So for instance, I talked to you guys earlier about if I had my hands and I wanted to warm them up, all I worry about is the initial temperature of my hands and the final state of my hands, how I got the temperature to move up. It doesn't matter how I got there, whether I rub my hands together to increase the temperature in my hands, or whether I poured hot water on my hands to get the temperature up. Heat and work are not state functions. They don't depend on the final answer or the initial, but this internal energy is a state function. Other examples of state functions are temperature, as I just talked about with my hands. If I want to increase the temperature of my hands from 20 degrees to 30 degrees, so I have to worry about where it starts, where it ends. Pressure and volume are also state functions. And we'll talk about state functions a little bit later. We talk about delta H, another unit as well, enthalpy. So we have here an equation for work. Work equals to negative pressure, P, times the change in volume, triangle. The change in volume is V final minus V initial, or V2 minus V1. And the convention we have established beforehand, work has a negative value if the system does work on the surroundings. So if you have, for instance, an explosion in a piston, it does work on the surrounding, it pushes the surrounding, you'll get a negative value. Example here, work done by the system on the surrounding, the expansion of a gas. We'll go through the calculation in a second, but the V final here will be greater than the V initial. Therefore, work is equal to negative P delta V, and the work will come out to be negative if V2 is greater than V1. So here is the example. A gas expands from 234 milliliters to 911 milliliters at constant temperature. V is a state function. So I'll just write state function here. I'll just write the word function for you. State function. So we're worried about, for state functions, how we start at the beginning and how we get to the end. Beginning to the end. It says calculate the work done in joules by the gas if it expands against a vacuum. So for the first time, we introduced the word vacuum, which means the pressure will be 0 in a vacuum. So if we have our value of P is 0, that means this term is 0, meaning the work done is going to be 0. So in this case, when we're working in a vacuum, if the gas expands from 234 mils to 911 mils, there's no work being done in a vacuum. The second question, what if we're against a constant pressure of 4 atm, 4 atmospheres? So we plug in these values, 4 atm and 911 for V2, 234 for V1. We do the math, we get negative 2708 atmospheres milliliters. We want our answer in joules. So I'm introducing now the unit conversion here to go from 101.33 joules for 1 atmospheres liters. So in this case, we would have to multiply by 101 joules on top, 0.33 joules on top. In the denominator, we would have 1 atm per liter. And if you notice, the liters will not cancel out. So you have to multiply through, and then you will have to divide by 1,000 to get it to liters, or I'm sorry, to get it to joules, so that the milliliters cancel out. And you'll get to negative 273 joules. So now we're going to try, let you guys try on your own. So you can pause the video and try. In this case, we have an air pump. If the gas has an initial volume of 2 liters, so our V1 is 2 liters. We apply constant pressure of 2.7 atmospheres, so P is equal to 2.7 atm, 2.70 atm. We have our volume, final volume, V2 is equal to 1.2 liters, 20 liters. So we plug in our values into work equals P delta V, and we come up with 2.16 liters times atmospheres. So we use our previous unit conversion that we just introduced, where 1 liter atmosphere equals to 101.325. So if we use our unit conversion, we would take the 2.16, we would put 101.325 joules in the numerator and 1 liter atmospheres in the denominator. We would get a final answer of 218.8 joules. Building on our internal energy, if we were to introduce a new state function, which is enthalpy, the best way is to describe it mathematically, where delta H is our enthalpy, and we have here energy plus pressure times volume. We can show that at constant pressure, H is equal to Q. This is at constant pressure. I'll show you. This little p means at constant pressure. We'll show you the easy proof on the next slide. We just defined that delta H, the enthalpy change, is equal to the internal energy change plus the pressure times the change in volume. If E is a state function, volume is a state function, delta H, enthalpy, change in enthalpy, is also a state function. If the change in internal energy is Q plus W, which saw this in the earlier slides, we plug this in here, we now get E, which is now Q plus W, plus P delta V. What do we know about W? W is equal to negative P delta V. Therefore, these should cancel off. So all we're left with is delta H, Q, and again, this little p means constant pressure. So we can extend the idea, if we're at constant pressure, which is a lot of the times we're working at atmospheric pressure, if delta H is positive, we say endothermic. If at constant pressure, if delta H is negative, we say we're exothermic. So let's say there's a change in enthalpy. We also have to look at the products again and the reactants. In this case down here, you can see that the products have a lower enthalpy than the initial reactants. Therefore, you're going to get a change in enthalpy where it's a negative value, and you get an exothermic reaction. Again, this is our example of photosynthesis, where we now can add a delta H in enthalpy reaction of 2519 kilojoules. So this was experimentally found that for this reaction, for 6 moles of carbon dioxide reacting with 6 moles of water, giving us C6H12O6 plus 6 moles of O2, the energy that is absorbed endothermic is 2519 kilojoules. Conversely, to make water, 486 kilojoules is produced. So we've been talking about using unit conversions, going from mass to moles, moles to mass, moles to molecules, molecules to moles. We can also use this 4 moles to energy, now that we have an internal energy reaction for each reaction, which we have to, each chemical reaction, which we have to give to you. So in this case, we have here 1 mole of carbon reacts with 1 mole of O2 to provide 1 mole of CO2 and 393 kilojoules of heat, which is released, which means you have a negative value here, released. The question is, if 4 moles of carbon reacts with 3 moles of O2, how much energy is produced? If you read, we have to use a limiting reaction situation here. So we have 4 moles of C, using our balanced chemical equation. For every 1 mole, so 1 mole of CO2 on top. For every 1 mole of carbon on the bottom, this gives us 4 moles of CO2. And we have to do the same thing with O2. So if we do the same thing with O2, 3 moles of O2, again a 1-to-1 ratio, and you'll get, as a result, 3 moles of CO2. So if we compare the two, 4 moles versus 3 moles, we can tell right away the limiting reactant is oxygen. So if we have 3 moles of O2 giving 3 moles of CO2 as our limiting reagent, again our limiting reagent is O2, we can now use this in a conversion to figure out how much energy. Just erase. So the question was, if 4 moles of C react with 3 moles of O2, how much energy is produced? We figured out our limiting reactant is the oxygen. So now we can take 3 moles of CO2. This is the new part here. We can multiply by 393 kilojoules for every mole of CO2. I got the 393 here. So how much energy is produced? It would come out to 1,179 kilojoules as our answer. The units will cancel. I want you guys to try the next one. Again, these answers are posted on the Common Blackboard site. When 4 moles of HI are produced, how much energy is needed? So here we have to kind of work backwards. We first have, I'll start on the left side, 4 moles of HI. We have to convert this to kilojoules. So we have 12.6. We get this from the reaction. Kilojoules. For every 2 moles, this is 2 moles of HI. Where am I getting 2 moles from? From our balanced chemical equation. 2 moles of produced gives us 12.6 kilojoules. When we work that out, we get 25.2 kilojoules. The next part, how much energy is needed to use up 8 grams of I2? So you have to use some of your chapter 3 knowledge. We first have 8 grams. 8 grams of I2. times mole of I. For every 253 grams of I. Where am I getting this 253 from? That is from the periodic table. So you can say 254 grams of I2. We then multiply by 12.6, which is given to us in the equation, kilojoules, for every mole of I2. The units will cancel, grams will cancel, moles will cancel. We're left with 12.6, kilojoules on top. When you multiply everything out, you get 0.397 kilojoules. So some points, which we will talk about later in this chapter. Enthalpy is an extensive property. If we multiply both sides of a chemical by a factor of A, then we must do the same thing for delta H. And we'll come back to this in Hess's law, but if we have to multiply this reaction by 3, if we multiply this reaction by 3 times 3, we must do the same thing to the energy, multiply by 3. The second rule, which we'll talk about, if we need to reverse a reaction. So now the reactants become products, so we have to reverse a chemical reaction. We must change the sign from positive to negative. And the third one, for reaction, delta H, the internal enthalpy, or the enthalpy for a reaction, depends on the state of the products and the state of the reactants. Calorimetry. Calorimetry is a measurement of the amount of heat evolved or absorbed in a chemical reaction or change of state. So in your labs, you work with calorimetry. You work with a high-end coffee cup, meaning that there should be no heat going in and out. There should be no matter going in and out. We have a heat capacity, which is the amount of heat required to raise the temperature of a given quantity of substance by 1 degree. And we have specific heat, which is an intensive property, meaning no matter how much of it we have or no matter how little of it we have, it will have the same specific heat value. And the units of this would be joules per gram per centigrade. So we have here specific heats of substances. We have a list here: water, ethyl alcohol, ice, etc. These will be given to you, their specific heats. What I wanted to point out here is, again, specific heat is the amount of energy you need to add to raise the temperature of 1 gram by 1 degree. So what's important here, the example I always like to use is the water. The Earth is usually mostly made up of water. So it has luckily for us, water has a high specific heat, meaning you have to add 4.184 joules of energy for 1 gram to rise by 1 degree, for the temperature to rise by 1 degree. If our planet was made up of gold, 100% gold, it would take much less, about 0.131 specific heat, which means you would add much less energy for the planet to heat up, which is important now in terms of climate change, that because our oceans are allowed to absorb a lot of water, it can actually save our or delay our temperature from the planet of warming up. So that's one thing to consider, that water has a high specific heat. versus the other metals such as aluminum, iron, copper, gold, and lead. Our unit conversion to go from 1 calorie to joule. Calorie is another unit of specific heat. Calorie per gram per centigrade. But to convert from calorie to joule, is 1 calorie is 4.184 joules. If I want to put this through an equation, I'll show you in the next slide. But you can imagine that if I had a beaker full of water and I had a bathtub full of water, the masses are different. I would have to add much more energy to the bathtub of water for the temperature to rise by 1 degree. I'll repeat that. I'd have to add a lot more heat, a lot more energy to the bathtub of water versus to the beaker of water for all of the water to rise by 1 degree Celsius. So mass is very important as well. We have this equation, Q equals ms delta T. Q is the heat that's transferred. M is the mass of our substance. S is the specific heat, which is given to you by those charts. And delta T is the change in temperature, TF minus TI or T2 minus TI. So the heat depends on the material, depends on the temperature change, T2 minus T1, and also the identity of the material, gained or lost. So for instance, if you have a piece of meat, let's say you had a piece of meat or piece of food, and you knew its specific heat, you would put it in a calorimeter. So you put the piece of meat here. You would light up the piece of meat, and it would burn, and you can measure the temperature change of the water before and after. If you knew the mass of the meat, and again, if you knew the temperature change, how much temperature change when you heated it up, or when you burned it, sorry, and you knew the specific heat of the meat, you could figure out Q in joules. And why is this important? Because a lot of times when you go to the supermarket and you pick up a piece of food item, you look at it, you figure out how many calories is in this food item. This is one way to measure how much food is in that, how many calories are in that food item using a calorimeter. So let's use our equation, Q equals ms delta T. Q is again the heat that's transferred, M is the mass, S is the specific heat, delta T is the change in temperature. So we plug in all the values. M is 200, delta T, a change in temperature of 10 degrees Celsius. We plug in those values. S is the value, specific heat of water, which will be given to you. We plug those in and we get 8.37 times 10 to the 3 joules. If the question, I want you guys to try the next one, calculate the specific heat of an unknown if 1638 joules raises the temperature of 125 grams from 25 degrees Celsius to 52.6 degrees Celsius. So again here we have Q equals ms delta T. We want to isolate which variable? We want to isolate the S, specific heat. So the equation will come out to S equals to Q over M delta T. So we would have equals to 1638 joules divided by 125 grams and T2 minus T1, 52.6 minus 25.0 This would come out to 0.474 joules per grams per centigrade. There are two types of calorimeters. The ones we talked about just now is a constant pressure, which means the calorimeter is working at the atmospheric pressure, and you'll do in the lab 2 styrofoam cups, you're adding an acid and base. And the other one is one at constant volume with a bomb calorimeter. We will not focus too much on the bomb calorimeter. But as I said, for the constant pressure calorimeter, which means the P will stay the same, atmospheric pressure will stay the same. You'll be doing this in the lab with the 2 cups and an acid-base neutralization. With the bomb calorimeter, this is an example where the volume stays the same. So the volume will stay the same. Here you can also measure the change in temperatures and also measure the heat transfer. And we'll stop there for part 1, and we will continue next time with part 2, Hess's law and heats of formation.